Before we begin, terminology is not standardized. This is the terminology I've chosen to use for this. Different people use different terminology. I'm not claiming this is the right one, but I do have to use it in a consistent way if I want to actually communicate something. Okay, so let's think about the very traditional view of adiabatic quantum computing. Is you map an NP hard optimization problem to a Hamiltonian, and the solution is an unknown ground state, effectively. And then you go very slowly. By the adiabatic theorem, you remain in the ground state with a high probability. And if you run for long enough and everything's completely coherent, you reach your answer with 100% probability. Very nice, very sort of theoretically satisfying, gives you effectively a deterministic algorithm. And, always succeeds, basically. But let's think about this a bit more, and think about it in particular in terms of actually doing something practical on a real machine. And let's assume that P not equal NP. So let's assume effectively that hard optimization problems exist. Pretty standard assumption, but let's make that. If you're going to succeed roughly 100% of the time, you're going to need your total runtime to be exponential, and you're going to need to remain coherent for that long, which in some ways experimentally is maybe not very appealing. Maybe you could imagine some kind of error correction in continuous time. There is progress being made there. Maybe if you had a very low temperature, dissipation could keep you there, but it would need to be very, very low. And the point is, if you really wanted this sort of theorist model of it to work, you need to mitigate all of the errors for a very, very long time. This is not what I'm going to talk about, but I've kind of put a wrench here to emphasize the idea of the sort of hard work associated with this. The other option is you could succeed with low probability in each run, and then you still have an exponential total runtime, so we're not cheating P not equal NP, but you could do each run very short and just become exponentially unlikely to succeed each run, but by statistics, your likelihood that you succeeded at least once will approach order 1 rather quickly. And this is conceptually not very satisfying. It feels a bit like you're playing the lottery. But when you think about doing this on a machine, on a real machine, it's much less demanding for coherence, because you only need to stay coherent for a time that's maybe sort of some weakly scaling polynomial in the number of qubits. What we do is sort of square root of the number of qubits, and that seems to work pretty well. I'll get onto that later. So what I'm going to argue in this talk is that for at least near term on any real device, this is actually going to be where you want to be. And the only real disadvantage is kind of compared to this approach, is kind of a psychological one, that it feels very unsatisfying. It feels like you're playing the lottery, and that the theory is much harder to do on this side, because you don't have adiabatic theorem anymore. So let's do a simple example. Let's think of a continuous time quantum walk applied to a spin glass. So what we'll do is we'll look at, starting with an equal superposition, we'll consider just a transverse field Hamiltonian, which, as I'll explain a little later, basically corresponds to doing a walk on a hypercube. And we'll have a problem that's just a Sherrington-Kirkpatrick spin glass. Just chose that because it's a well-studied example. Well, actually, we slightly modified it by adding some field terms to break some degeneracies. But it's a well-understood problem, and it's thought to be a good model for sort of hard optimization problems. And if you do this, you get some complicated mess for what your success probability is. So if you say, okay, well, instead of we'll just measure at a random time, and that will smooth out some of this messiness. So we're not accidentally hitting in one of these values. Yes?
Sorry, where is the quantumness coming in your Hamiltonian problem? Because
Because there's a typo, and that should be an X. That's where that's coming from. Good catch. Yes, that should be an X. And then if there weren't that typo, that's where the quantumness comes from. With that as a Z, you're absolutely right. It would be completely not quantum. So, okay, first typo in slide spotted. Hopefully the only one. No, it's fine. All right, so how is this a walk? Our sigma Z, or our sigma X, not sigma Z, apologies for the typo, corresponds effectively to a hypercube. You can basically imagine this as every bit corresponds to one dimension, and if you're on the right side, it's a 0. If you're on the left side, it's a 1, or top bottom, or as many dimensions as you want. Beyond 3, it becomes hard to visualize, although later on I'll show you one I've drawn in 60. And so then, how might this help you solve a problem at all? Well, because it's a closed system, energy is conserved. And so, if I've started out in the ground state of the hopping Hamiltonian, of this, which is just an equal superposition of everything, then if my total energy is conserved, and it's just the sum of the expectation value of a sort of kinetic term and a potential term, if the expectation value of your kinetic term goes up, which it can do nothing else, the expectation value of your potential term goes down. So, on average, you're doing better than optimal. You're doing better than random guessing in terms of the optimality of your solution. Now, this doesn't say anything about the probability of finding the one right answer. That could go up or down or whatever. We find numerically that on average it goes up, but there's no theoretical guarantee that it would, at least none that we can figure out. So then here's just a plot of what the energies are doing. Here's the energy of the driver going up and energy of the problem Hamiltonian going down, and the total of them equals 0. They sort of mirror each other. So let's look at how well, so now there's one more bit that I need to discuss, which is I've had this parameter in my Hamiltonian, which is sort of how strongly you hop, this gamma parameter. So I imagine I just have this Hamiltonian, I turn it on, rather than in an adiabatic routine, I just turn it on to a constant value. But what is this constant value? How much of the hopping do I put in versus the problem? And is there a way we can find this without cheating? Do we have to do something that's equivalent to solving the problem to be able to find this? This is a problem with avoided crossings often, is if you could slow down for them, you could get a speed up, but you don't know where they are. In this case, though, for this quantity, if we look at the success probability after a long time, it follows, which we can calculate analytically in a way I'm not going to go through, you find a very broad distribution. And what we find is, yes, in fact, we can find a good heuristic for choosing this value. Honestly, how we found that heuristic and how it works is not a very interesting story. So if you really want to find out about it, read our paper, but I'm not going to talk about it here because effectively you're just matching some spectral widths and then you add in a fudge factor and it seems to work. But yeah, not worth going into. So now if we look at the scaling of our success probability, the scaling of our probability to find the right answer, these are small problems, so we can just exhaustively search to find what the right answer is, and say, all right, let's run many of these and look at the probability of finding the right answer after a short random time or sort of the long time average. And we look at how that scales with size. Again, at the sizes we can numerically access, which is up to about 20 qubits. So what we find out is we get a nice straight line for our scaling, which in some ways is maybe unsurprising because these are kind of all thermodynamic quantities. You kind of think it might, in some sense, equilibrate to something nice at relatively low sizes. And we look at our scaling, and we get a scaling that's 0.417 on our success probability, which you can think of as inverse runtime. So our runtime scaling is better than doing a Grover search, which, okay, at first that seems like some kind of magic, but remember that this is a type of problem where there is structure to it. And I'll go on to that later on. And there are actually classical algorithms that beat the Grover speed up on spin glasses. So there's no sort of, we haven't cheated any fundamental information theoretical principles by doing that. So if we look at this a little bit deeper, here in this plot, you can't see it because they overlap so well. There's actually two curves that overlap in this one, which is the success probability at long time and the success probability at a time which goes as the square root of the number of qubits. And so this suggests that what we're having is something where there'd be no point in waiting for longer. Effectively, you're reaching equilibrium very quickly. So if you're thinking of this system as sort of a quantum spin glass, okay, there aren't really phases because we're at a finite size, but we're probably in the precursor, our gamma values we've chosen are probably in the precursor of a paramagnetic phase rather than a spin glass phase because we're equilibrating in a pretty short time. And we can see we're equilibrating because the infinite time average, which you can calculate using some mathematical tricks, and the average over a short time just sit right on top of each other. And yeah. So I mentioned before the importance of this correlation, and this is how we know we can do better than a sort of root n speed up, because it's not unstructured. There is structure there. And so we can ask, well, how does this compare to unstructured problems? Well, our scaling is already one way we know. But let's look at a random energy model, which is a model where you assign each bit string an energy independent of what the energy of the other bit strings is. So you pick out a bit string, say 0, 0, 0, pick out an energy for that, 0, 0, 0, 1, completely independent energy, keep doing that. And what you see there, well, first off, there is no structure. So classically, the best you could do on a random energy problem is just through guessing. And quantum mechanically, what we see is we see sort of search-like dynamics. What we see is as you scale up the size, this measure of sort of the width, it's a full width half max of the distribution of long-time success probability, scales down very quickly. And this is somehow not surprising. It's very reminiscent of unstructured search, where you have to choose your parameters very, very precisely, which is another disadvantage of doing these sort of Grover unstructured search type algorithms, is your parameters tend to be need to be very well chosen. Whereas for our spin glass system, there's a wide range of parameters you can pick and all do pretty well. And this is probably why our heuristic for selecting these values has worked, is it's a pretty forgiving system, actually. And so, as I promised, we'll be discussing unstructured search. So what we have here is actually very much like when you have an unstructured search. So an unstructured search is you just have a marked state, a single state you've given a lower energy, a single bit string. Every other bit string has the same energy that's a higher energy. And what happens there is you need to run a long time to actually see any speed up, and you need to do a single long run. Or, I mean, technically you can do more than one, but you need to run for a long time, a time proportional to root n with every run. You can succeed with probability order 1 after this runtime. And this seems to be what we see with the random energy model too, but there you have to carefully select, or it's not obvious how you choose the parameters to get this success probability that goes up. Amazingly, what you see here is the success probability actually goes up with size and approaches 1. So You might say, okay, so this unstructured search is interesting, but it's not really implementable. So I'm going to give a quick aside to say that you actually can at least build a sort of proof of principle model of this unstructured search, basically reviewing what's in this paper, just as a short aside, and then I'll come back to the main story. Basically what you can do is you can use the permutations, the fact that they're permutation symmetric. You put you have n spins, little n, then you put n auxiliary spins, and you can arrange couplings and fields so that those effectively count how many of your logical spins, logical variables are in the one configuration. And using that count, you can then assign penalties to that count and build effectively an unstructured search problem. In that case, the state you have to mark is 0, which means that you can model the dynamics, but you can't really have an unknown marked state. But in any case, this isn't necessarily a real algorithm so much as a test bed. We've looked at how to implement this in this paper here. We look at how you could perturbatively get search dynamics out of this using Rydberg atoms. There's probably other implementations. If anyone has ideas for experimental implementations of this, I'd be happy to either talk to you, or you could also just read this paper that explains all of it. But basically all you need is two-body couplings, sigma z and sigma x terms. All right, so now let's go back to our spin glasses. We've had a bit of a detour on unstructured problems and how they're different. Let's go back to structured problems, to problems where the energies of bit strings are correlated. And say, okay, why is this interesting? And is this really just a one-off, or two-off, I guess, comparing our spin glass to random energy model? And what we've found so far is no, there really do seem to be these two types of behavior. Either when you have some structure and do a quantum walk, you see a success probability that exponentially decreases in each run with system size, but you can get it in a fast runtime. If you don't have structure, you tend to want a long runtime. You have very sensitive choice of parameters, and you have to stay coherent for a very long time. And we looked at that a few different ways. We looked at one way of removing effectively correlations is to change our driver Hamiltonian. So instead of having bit flips, instead of having these sigma x's, having a hypercube, look at a complete graph, where if you're in one state, you can go to any other state. And if we do this, what we see is it recovers search-like behavior. So this is long time success probability. If this goes back up, you get sort of unstructured search-like behavior. If it keeps going down, you're getting this other behavior we see. And so what we see is we can then recover that kind of behavior by changing our driver Hamiltonian. I know there's some more work going on whether or not you can choose the parameters on this. I talked to Leonardo Novo a while ago, and he's looking at this. We can do a few other things. You can scramble the energies. Again, you get that. And the other thing you can do is if you take the random energy model and you order the energies in a gray code, you recover not the sort of structured type behavior we have here. So it's not just a one-off difference between our spin glass and random energy model, but more general. So far I've just been talking about quantum walks. My title is Quantum Walks and Rapid Quenches. So far the scaling I've given isn't very impressive. It's actually sort of similar scaling to a good classical algorithm. So far I haven't actually, I've shown some things that maybe elucidate some of the mechanisms, but don't actually tell us anything interesting about, or don't actually give us an interesting algorithm. So can we do better? So what we can do is we can say, what if we add, instead of just doing a quantum walk, we add a rapid quench at the beginning. So do something like adiabatic, but we effectively, before we get into the spin glass regime, we just stop and turn it off and don't bother with that region where we know there's going to be exponentially small gaps and other badness, and just say, okay. And then the other thing we could try, which I'll talk a bit about, is to use as a subroutine along with classical computation, which I'll just cover a little bit. But first, let's talk about these rapid quenches and what we saw numerically when we did that. So, first off, is there a theoretical argument similar to this energy argument I gave for a static Hamiltonian? It turns out there is. What you can do is you can effectively trotterize. And you can say, all right, let's imagine that I can model my evolution as an infinitesimal step where in one step I change my Hamiltonian, in the next step I run for some time, change it instantaneously, run for some time. And yeah, this is known to mathematically converge. It's a Trotter decomposition. And what you can see is at each of these steps where there's the evolution, you have the energy conservation argument from before. Because you're starting, at least for the first one, you're starting in the ground state of your driver, so energy has to transfer from your problem. But then something else clever happens. If I rescale time, I can always make it look like a quantum walk. If I just rescale the time by the inverse of the constant in front of my problem, it always looks like a quantum walk. And I'm always scaling this down. So effectively, the energy in my driver is getting scaled down and down and down and down. And so after my first run, I have some energy goes into that, and then that energy is scaled down by some amount proportional to this. And then even if all the energy went back into my problem, I'd still have a lower energy. And I can keep repeating that argument and argue again that on average, this work with Adam Callison and Viv Kendon, as most of the work so far I've presented has been, we can argue that after this rapid quench, my energy on average is going to be lower. Again, I can't say anything theoretically about success probability, about probability of finding the one right answer. At least I can't figure out any way to do that. But we can do numerics, which is what I'll talk about. But first, let me give some examples of how this works and sort of some motivation for this mechanism. So if we think of a simple example of just sort of two trotter steps, so I do a quantum walk, change my parameters, do another quantum walk, what I can see is, indeed, I have, like I had before, the effective expectation of my problem Hamiltonian goes down, expectation of my driver Hamiltonian goes up, energy expectation. I change the parameters, this stays the same, this goes down, and then it can absorb more energy, and this goes down further. I see, at least in this one example I've looked at, which is just an example small spin glass problem, my success probability indeed goes up at this point. Okay, that's just a one-off example. Now, of a simple version where I've just had a single step, I can also look at if I do a quench, non-instantaneous quench, do a sort of pre-anneal, and what I can see, these are sort of busy plots, but effectively blue, red, and then purple are going to longer and longer time for the pre-anneal, and I see I'm dissipating more energy, more expectation of my success probability, or of my problem Hamiltonian, and I'm succeeding more and more. These dashed lines are where you end the ramp and start just doing a regular walk. And so, okay, this is kind of cool, but I've only showed it on one example. Maybe this is a pathological example. Maybe this doesn't do anything in general. Maybe in general, my success probability actually goes down and is worse than guessing. Let's look at it numerically. So, if we look at this numerically and look at the scaling and say, all right, what is the scaling we have if we now consider one of these pre-anneals? So, again, a kind of busy plot, but the takeaway is basically these black and gray lines, which is our success probability scaling if we've now chosen an optimal gamma for doing this pre-anneal. And what we find is there's two slightly different ways of selecting it, which is why there's two lines, is a scaling exponent on the probability that's like 0.0145, which is quite good. This green line is, okay, I've inverted it to turn it into a probability rather than a time, but is a representative of the scaling of branch and bound, which is a sort of high-end classical algorithm. So now we're beating a high-end classical algorithm by quite a lot, at least in our finite size scaling. This was work done by Zoe Bertrand, a summer project student, to implement the classical branch and bound. Now we can ask, all right, what happens if we look at a quantum algorithm and compare this to a different sort of state-of-the-art classical algorithm? And so there's a quantum version of branch and bound, not in our work, but you can find it in this paper here. And they get a very similar scaling to ours. Technically, theirs is slightly worse, but given that this is finite size extrapolation, I would consider these about the same. And one thing that algorithm does that ours doesn't is that's actually a classical algorithm with a quantum subroutine in it. And so it uses a classical branch and bound approach, but then inside of it puts a quantum subroutine. Whereas what we've done so far hasn't been hybrid at all. So there's the hope that maybe we could make ours even better if we did it on top of a hybrid quantum classical subroutine. So it's probably now worth discussing. We haven't actually done this, but at least not for this ramped pre-anneal, how you use continuous time protocols as a subroutine. There's been a fair amount of work on this with gate model, but relatively less with continuous time. But there's still some, and there's actually been some experimental work onto it, as I'll get into. So there have been 3 sort of methods that have been considered. There's dissipative reverse annealing, which is actually implemented on D-Wave devices, which again, highly dissipative, but you can actually get at doing experiments with them. So I'll talk about some experimental data on one of these a little later on. But this isn't really what we want for what we're doing, because we're considering a coherent protocol. So this won't work for us. There's a Mexican hat schedule, which was proposed by Perdomo Ortiz et al. That one isn't compatible with the proofs I gave a few slides ago, or the sketch of a proof I gave on how these sweeps reduce energy, because it involves 3 separate Hamiltonians. And then there's a bias driver Hamiltonian idea by Tobias Grass and also by the authors of this Chinese physics letter paper, which is compatible with what we've shown before, and I'll discuss that later on. Before I do, I just want to quickly discuss some experiments that have actually been done with this, because you can actually do experiments on this because there's an actual device. So one thing you can do is you can say, okay, first, do these hybrid subroutines actually work? In other words, what you'd really want for a hybrid search subroutine is you'd want to be able to bias yourself toward a good guess at a solution and preferentially search around that guess. That would be maybe not the only way to build a subroutine, but certainly a way. So the question is, if I mock up an energy landscape like this, if people want to hear about how I got this from an Ising model, I'm happy to discuss it. If people don't, I'm happy to skip it. I have some bonus slides on it, though. We can figure that out later on. But if you make a landscape where you have a false minimum here, a true minimum here, and you start sort of in Hamming distance sense near your true minimum, but far from your broad minimum, and this S prime parameter is effectively going this direction is how much you search. So this direction is searching a lot, this direction is searching not a lot. With this nice color-coded diagram, you can see if you search a little bit, you just stay right where you are, stay in that local minimum. But then you can get to this local minimum without getting trapped in this false minimum. But if you go too much, you get trapped in a false minimum. There's a little regime here where you can sort of get stuck. But this is actual experimental data on how this works. So then if you look at, okay, people have now looked at also using this algorithmically, again in a dissipative regime, so it's not directly relevant to what I've been talking about before, but just to give you a flavor of the idea that you can get something interesting out of hybrid subroutines. And there's tons and tons of papers. And if you look at these, here's a quantum simulation paper where the simulation seeding with previous states actually made it possible. Speed up of 100 times, things like that. Forward annealing, meaning not biasing, you couldn't solve any. Doing some simple biasing, you could solve most using an iterative method, et cetera, et cetera, et cetera. So there's quite a bit you can actually get ahead with these in real experiments, but in a dissipative regime. So now let's talk about theoretical non-dissipative protocols, which there's not a device to implement, so haven't been implemented. But the idea here is if you want to bias toward a solution, and this is detailed in these two papers, if you want to bias toward a solution in a sort of quantum, either adiabatic or quantum walk type search, what you can do is you can make your field, your initial driver Hamiltonian, not completely transverse, meaning you bias them. You bias each of these fields by an angle. So instead of just sigma x, there's some sigma x plus some sigma z. And the sigma z, you give a plus minus sign based on each one, based on which solution you want to bias toward. And then you start in the ground state of this, which is now a biased probability distribution. So you're starting in a probability distribution that's biased preferentially toward a guess, rather than being a completely random, unbiased distribution of bit strings. And yeah, and this, we can look at how well this works in a sort of proof of concept numerics experiment. So one question you can ask is how good does your guess need to be before it's worth using some biasing? In other words, if I have a guess, and because we want a simple example, let's consider guess with independent probabilities of each bit being right. Meaning, if I have a 45% probability of being right, each bit independently with sort of, or 45% probability of being wrong, 55% probability of being right, 55% it's the right solution, 45% it's the wrong one, and then I do each one independently. And then I say, okay, I have this probability to be wrong. When is it worth this theta here? Parameterizes, that's this angle here. It parameterizes how much I'm using my guess. Obviously, if I have a perfect guess, I just say, I already have the answer. I'm not going to bother with my quantum machine. That's not a very interesting protocol. But if I have a guess that's less accurate, this is looking at a small size, like I think 8 qubits, then is it worth biasing toward that? Or is it better to just use a standard transverse field? And what we find is right around 50% probability to be wrong, meaning when you're just a little better than random guessing, it actually starts to become worth biasing a little bit, which is interesting. This isn't really the end of the story because in any real protocol, your probabilities of different bits being wrong will be correlated, but we just want to do something simple to model that and to argue that maybe there is something you can get out of these hybrid protocols. This is just with quantum walk. We haven't looked at doing ramps with this yet, but this is preliminary work done by my grad student, Laura Nita. And so now, at least for the main talk, that's sort of what I wanted to get across. And so take-home messages is, unless P equals NP, doing these sort of psychologically unsatisfying types of protocols is probably actually what you want. Because you need so much less coherence time. And they seem to work pretty well. It seems that you actually do pretty well by doing sort of short run times. We also found lower precision is needed. So even if you could somehow deal with the coherence, if you had something that uses unstructured search type dynamics, you actually look at the way that single avoided crossing works. If you're doing adiabatic, your anneal schedule has to be exponentially precise where you slow down. If that's off by a little bit, and that little bit reduces exponentially, then you're no better than classical random guessing. Quantum walk, where you do your walk, if you're off by exponentially small amount, you're no better than guessing. And yeah. And so that's a big part of the argument I wanted to make here is, even though I think in the past people have kind of said, well, algorithms with exponentially low success probability, we don't want to go there, that actually probably is exactly where you want to go if you want to think of doing things on real machines. And then quantum walks on spin glasses, what we've seen with this. First, we've seen correlations in the energy landscape do play a role, which this is important because, well, one, it's less demanding for control precision, as I already mentioned, but you also see a lot of papers where people argue that, okay, let's do something with an unstructured simple search, that's what SS is, simple search, and then we'll use that to argue that that's how all continuous time quantum computation is going to work. What we found actually in this work is no, we get qualitatively very different behavior when we look at a realistic problem versus simple search. And so all these papers going back that say, okay, we found this, this, and this for simple search, and then try to draw conclusions for how sort of rapid quenches are going to behave or something like that, all of that should probably be called into question because the dynamics are just very different. And there's no reason to think that anything you might say about simple search would carry over. Our pre-annealing work seems to be pretty competitive with the quantum state of the art. The quantum walk bit, it's interesting for understanding the mechanisms, but as an algorithm itself, it's about competitive with the best classical algorithm, so it's not that interesting from an algorithm perspective. And we're working on hybrid subroutines, but that's very much a work in progress. And with that being said, that's at least what I've had to say for the main talk. If people are interested, I can give the details of this, but probably first it's better to sort of open up for questions, and then if there's time and people are interested, I'll go into how I constructed those experiments. If people aren't interested, I won't be offended. Some people are interested in Ising models, other people not so much. And if this is a group of people who not so much, then I won't bore you with it. So, any questions, comments, concerns? Yeah. Well, I think for the recording,
Okay.
it's probably better to have the microphone.
When you do these quantum walks on spin glasses, I always get a bit confused because the reason you cannot find the true ground state of the spin glass is not really an algorithmic problem, it's a physics problem. The spin glass in nature behaves like that, so why do you think that you can find an algorithm that is efficient enough to find the true ground state that doesn't even exist in nature, yeah?
Well, so one thing is we've looked at very small versions. So this is absolutely a very good point. On any real optimization problem, as long as we believe P not equal NP, realistically, you're never finding the one right answer. If you think of like the glass that comprises those windows, it's never finding its ground state, doesn't matter, or maximum, minimum free energy state, doesn't matter, lifetime of the universe, just not happening. And it's similar for large optimization problems. What you're really wanting to do is to do better than the other algorithms out there. So do better than the best classical algorithm. Better could either mean you find a good solution faster, or you find the best solution, but you find it or you find a better solution in any time, or in any reasonable amount of time you find a better solution. However, what we have access to numerically is small sizes. And in small sizes, the easiest thing to analyze is total success probability. But you're absolutely right. In a large-scale spin glass problem, realistically, you're just not finding the one true answer. But you're okay, because no one else is either. So you're really trying to sort of do better than the other guy. But that's much harder to analyze numerically. And so what we've analyzed numerically is this success probability. And yeah. So no, absolutely. The long time scales associated with a glass phase, we appear to have gotten around because I think all of this appears to be operating in a precursor to a paramagnetic phase where dynamics can be fast. At least that's kind of what this suggests, because if we were in the precursor to a spin glass phase, we'd expect, if we waited a polynomial amount of time and averaged, it wouldn't look like a long time average.
And can you relate the success probability that you get? Can you relate it to how your energy landscape would look like? Would you expect, for example, that your success probability is going to be much lower if I am studying a problem with one of these algorithms that has a lot of local minima? Average is very small, or I mean, do you have the same problem that Monte Carlo has, that it gets stuck?
So yes, so the question was, do you get stuck and there's a lot of local minima for the recording? Do you get stuck when there's a lot of local minima, and have we looked at different energy landscapes? And we have a little bit. We haven't really exhaustively gone through and understood it. I mean, I suspect it would have the same problem. There's no free lunch. This is definitely going, I mean, our success probability goes down exponentially. A lot of that probably does have to do with getting stuck. I didn't include it in the talk because the results weren't really that interesting. We have looked at effectively something like a Sherrington-Kirkpatrick spin glass, but where we take all negative values, so it's totally ferromagnetic. And what we found there is our success probabilities in general seem to be higher, and our scaling is not as bad. Although it does seem, the success probability still does seem to scale down exponentially, which just tells us that's not a very good algorithm for that kind of problem, because Monte Carlo could solve that easily. But maybe it is for spin glasses. We've also looked at certain sort of constructed toy problems. And what we found there is some constructed toy problems, you can make the success probability for an adiabatic routine arbitrarily low, as small as you want, basically, the runtime, by making the gap effectively as small as you want using some sort of tuning knobs in the Hamiltonian. And the quantum walk probability, you can tune the adiabatic probability down by 15 orders of magnitude, and the quantum walk probability goes up by half an order of magnitude. But that's sort of one pathological case, not a class of problems. So yes, there is going to be a lot of interesting connections with the energy landscape, and we've scratched the surface on it, but we haven't totally understand it.
Okay, and I will ask the last one.
Oh yeah, of course.
Stop, but, and how does this connect with the fact that since you're in a finite system, you have a finite size cap, and when you make the system bigger, this finite size cap should, in the thermodynamic limit, should disappear, right?
Well,
so it seems that this should be connected to your acceptance probability to just...
So that's true. One thing to notice is we have scaled our runtime polynomially. So yeah, we would expect that you probably want a mildly scaling runtime rather than just a completely non-scaling runtime. We don't think that necessarily the minimum gap is actually really a determining factor here, because the dynamics here involve many, many energy levels. So sort of with one thing that makes traditional adiabatic so appealing is it's theoretically approachable, because you have this two-level model. Here, if you look at the occupation of energy eigenstates, you have all of them. I mean, not really all of them, but you have, maybe the bottom third of the spectrum's occupied significantly or something. And so your dynamics are just completely different. So what we think we're having is somewhere where the gaps are sort of scaling down polynomially but that's still leading to pretty fast dynamics. And what we're really thinking there is probably that's because if you go to a large size limit, this is probably right on the edge of the spin glass regime, but on the edge of it where you're still in the paramagnetic regime. And there's some questions. I'm not an expert on spin glass phase diagrams, but some people have suggested there's actually two paramagnetic phases, and it's possible that this wide peak, the width of that actually doesn't go to 0, but the width of this precisely corresponds to the width of one of the paramagnetic phases. I'm not going to pretend to be an expert on that stuff. That's just a paper we found and we went, that could be an interesting connection, or maybe it's dumb. But the referees haven't said it's dumb, so yeah. Yeah.
Yeah. So the question is, if you do this pre-annealing on physical device like D-Wave, let's say, usually what they do, they propagate the state for too long, and then everything is pretty much thermal. But what if you take annealer and propagate the state just a bit, so you pre-anneal, and then repeat it many, many times? Do you expect that the success probability in total will grow?
Maybe. So yeah, running very fast so you can get into a coherent rather than dissipative regime is, I think, something that should very much be a goal for quantum annealing. And we're not there yet. I think D-Wave actually very much wants to do this. At least from a traditional adiabatic perspective, you think you'd want to run as long as possible. But actually, there's actually an experimental limitation on D-Wave devices, a lower limit on how fast you can run. And it has to do with some active correction you have to do on the circuits, on the superconducting circuits. So there, they actually can't run as fast as they would like to, because they would love to do exactly what you're describing, where you run so fast the dissipation doesn't really have an effect, and you're succeeding with a low probability, but you go many, many, many times. Unfortunately, they can't really get into that regime right now. It's more in the dissipative regime, which I haven't had a chance to talk about. There's actually probably a lot of reasons to think there are interesting things in the dissipative regime. It's just much, much more complicated. Like here, there's something that's complicated and probably you can't say much theoretically. In the dissipative regime, it's just even worse. There's just nothing. So yeah, but yeah, absolutely. Getting from I think for sort of continuous time methods, getting from a dissipative regime to a coherent regime should be a high priority on experimental goals, and I think is for a lot of people who work on this.
So for instance, if you MIT setup or Google setup where they claim to have like smaller number of qubits, like 100, all coherent, but obviously you cannot do completely adiabatic. This will be the strategy to use.
Yes.
Okay.
Yes. So I think these kind of strategies, I think in some ways, this is maybe without saying it, a lot of the experimental people have always sort of been thinking in these terms, and the communication sort of hasn't been there. The experimental communities have more thought in terms of what you can do experimentally, and the theoretical community has thought more what you can approach theoretically, which is adiabatic limit, and there's sort of a disconnect. And trying to sort of bridge that disconnect and say, okay, even if you ignore open system effects, it's really hard to say anything in a rapid quench regime, but maybe we should try. And that's I think, a big part of this talk. And if you have any ideas on something that can be done theoretically there, would love to hear them.
Thank you. And I actually have one question about the very slide you show now. Do you know the reason why you actually should include the driver Hamiltonian, so sigma z terms, can't you just start from the ground state, which is superposition of your guess and like all the rest, and only do the sigma x driving? Like,
so I don't think I completely understood the question. Start in a ground state that's a...
okay.
So just...
Start not in the ground state.
Not in the ground state.
Yeah, yeah.
Okay, so the reason that I'm going to claim you want to start in the ground state is because of these energy arguments. Because you have these arguments that if you're doing time evolution and you're starting in a ground state, then you're effectively, your energy expectation is going to flow from the problem to the driver Hamiltonian. And that's in some ways a fairly weak theoretical argument because it only talks about on average, but at the same time, it's at least something. People have looked at not starting in ground states. I don't know if I cite the paper, actually. I don't think I do. There's some work by Baldwin and Laumann, and actually also some work the Google group did, where they look at starting not in a ground state. And what they find there is you can do interesting things, but what tends to happen is you don't preferentially go toward more optimal solutions. You go half the time toward less optimal, half the time toward more optimal, roughly. However, that could still work because you don't care about the ones that are really bad, and it's easy to compare optimality of solutions. So people have looked at this. There's a Google paper on what they call population transfer, where they look at this in quite a lot of detail. What they look at there is effectively a protocol that would run for a long time, but where you have a sort of mini band up above of higher energy states, and then you have a few optimal solutions, and look at can you effectively transfer from one local minimum down here to another one of the same energy, and then do a hybrid routine afterwards where maybe you do a classical search and find something lower. And there's some very interesting work done on that. Their paper is incredibly technical and has a lot of condensed matter theory, but it is quite interesting. So yes, there is some interest in that. Where we're interested in is more doing these ground state tricks, but that's by no means the only thing you can do. And people have looked at not starting in ground states.
Thank you.
But correct me if I'm wrong, what you're doing here is you take ground state of Hamiltonian and then you quench another Hamiltonian and let time evolve.
Yes, so the question is, here we start with one Hamiltonian and then we add another one in time evolved. And yes, so effectively, that is what we're doing. We're having a ground state of a Hamiltonian made of fields, but where the fields aren't completely transverse.
Sure, no, my question is because this looks like a typical thermalization problem where you're just waiting for your system to thermalize and see where you lead to. But what you thermalize to is very highly dependent on the initial state.
Yes.
So it might be that for one initial state you have a very different thermalization than for another. Especially if you're watching your Hamiltonian.
Yes, so the question was, how does the thermalization depend on the initial state? And it seems like it depends a lot. And I would argue, yes, that's kind of the point here, is to use this as a hybrid quantum classical subroutine. So the overall goal would be to have some smart classical subroutine to choose a smart guess, and then bias toward that smart guess, use a search there to find hopefully another good solution, and maybe iteratively do that. There could be arguments that even using a random guess, you could come out ahead, because in some cases you'll get stuck in sort of broad local minima. And then even just picking states at random, you might win. And that's been thought about. That is discussed a bit sort of in this paper, but in a different context.
Okay, so I think I have also one more kind of general question. It's about, so I've seen that you compare kind of classical algorithms between quantum algorithms. So people are kind of wondering on the theoretical side, so when are you actually better than classical algorithms? And so one could ask even a more kind of more difficult question. So when on a practical problem you actually reach something with your possibly hybrid algorithm, something better than the classical side. So what is the status here with respect to the problems you are considering?
Well, so I think the status in terms of practical problems is, well, looking at these small sizes with practical problems, I can't really see a way of doing it because your numerics are just limited to such small sizes. Experimentally, the only real devices you have for this are sort of D-wave devices, and there you have really nice, what I would classify as really nice proof of concept, but you're probably not there yet. You've just, but yeah, absolutely. I think looking at practical algorithms for actual real problems, so not just sort of, okay, I have a spin glass and that's a model of an optimization problem, but no, here's an optimization problem people actually care about, and if I get a better solution, I win, is an incredibly interesting sort of field of research and area. I haven't talked about in this talk, but it is something I've looked at a fair bit. And there are, I think, actually quite a lot of relatively simple gains that can be made in that direction, including just how do you map discrete variables to, and I don't have a slide on this, unfortunately, but how do you map discrete variables to Ising models? And it turns out if you're looking at a problem that you have to actually embed in a device, encoding that as the location of a domain wall works much better than doing the traditional optimization approach of having a one-hot encoding, where you have a highly connected graph and that encodes so that just one of them lights up. The less connectivity, when you then on top of that consider that you have to embed into a real device, makes a huge difference. But absolutely, thinking about real problems is where this has to go. And unfortunately, I didn't have time to talk about work in that direction, and I haven't really put that in my talk. But that is something I think about, and I'd be happy to chat more about that sort of offline.